have two things to talk about. Subspaces, and I'm going to talk about a couple of very elementary properties of vector spaces, mainly to illustrate what I expect from you for a proof, what a proof looks like, and what a careful argument that one thing is true or something is equal to another looks like. First of all, subspaces. Second, properties and proofs. OK, so first of all, we'll do subspaces. Let V be a vector space. So we all know the definition of a vector space. It's an additive abelian group with a scalar multiplication or field action. It's commutative. Associative has additive identity, additive inverse, multiplicative identity, and distributive properties. We're going to define a subspace in terms of a subset and the definition of vector space. So a definition, a subset U of V, this vector space. And by a subset, I hope you all know what I mean by that. Just in case, we mean a set U with a property that any element of U is also an element of V. So a way to define what a subset is. A subset U of V is called a subspace of V if U is also a vector space. And we want not just that it's a vector space, but that it's a vector space with the same structure as V. So that means it has the same addition. Remember, addition is just a function from V cross V back to V. That's the additive abelian group addition, and the same scalar multiplication. And that was this function that goes from the field cross V back to V. Now, can a subspace of a vector space V be a vector space over a different field than V? No, right? Because it has to use the same scalar multiplication. So it has to use the same function here, the same f. OK, so they're over the same field, which is why I didn't really say that. Okay, they're over the same field. Here's an example from finite dimensional land. Let's let V be the vector space F3. So triples of field elements with element-wise addition and broadcast multiplication. And let's let U be the set of vectors of the form x1, x2, 0, x1 and x2 in the field, and 0, the 0 of the field. Now this is a subspace of V. You can see that because, well, in particular, each of these is also 3 elements. And the idea is that, well, it's a vector space because if I just forget about what 0 does, because it's not important, this is also going to be a 2-dimensional vector space. But that's not a formal way of saying it. We'll get to that in a second. OK. So U, which is the subset, shares elements. It also shares this addition. It also shares this scalar multiplication. So once we know that we're looking at a subset and we're using the same functions, we already know a lot about U. And so it's easier to check if it's a vector space. It's easier to check the axiom. So naively, when you look at this definition, you think, oh, no, I'm going to have to check all of those definitions to make sure that it's also a vector space using these things. But because it shares so much structure, we don't have to really do all of it. We can simplify that. So we're just going to check the following. And this is really a theorem, which I think is the way it's presented in the book. But we're going to call this the subspace criterion. That is, there's only three things I need to check. One, the zero vector of V, the bigger vector space, is in this subset. And that's sort of an additive identity property. Secondly, we need to check that if U and V lie in U, then U plus V also lies in U. And you could think about this property as saying that this subset U is closed under the addition law that it inherits from V. And the third thing that I need to check is that if A is a field element and U is in U, then AU is also in U. And analogously, we say this means that it is closed under scalar multiplication. Right. I mean, you could think about it as this couldn't possibly be a vector space if these failed, because these operations won't even be defined when I replace V with U here. Right. And these first two axioms are what makes it into a subgroup, and this last axiom is what makes the field action work. Because these first two don't mention that, right? Okay, so let's say quickly why the other axioms of a vector space will also hold should these three points be covered. So commutativity we want that for all U and V in my vector space, U plus V equals V plus U. So why does that hold? Why don't I need to check that in this list? We're doing addition in this big vector space V. We're using the same function. Any ideas? Well, we know it holds in V, right? We know it holds in the big vector space. And these two elements are also elements of U. They're also elements of V. And so if these two things are equal in V, they must be equal in U. They both refer to the same element. So you can think about this as kind of inherited from V. That is, it's true because it is true in V. And because it's closed under addition, right? So closure under addition means that U plus V is also in U, right? Because if it wasn't closed under addition, we couldn't be sure that this element, which we know to be an element of V, which is equal to this element of V by commutativity in V, was even an element of U. Okay, so closure under addition and the fact that it holds in V means that it holds. How about associativity? We had two associativity axioms. U plus V plus W equals U plus V plus W. So this holds for the same reason. Right? So long as V plus W and U plus V plus W, U plus V and U plus V plus W are all in U, we can be sure that because this holds among elements of V and the addition is the same, that this will hold among elements of U. Okay, so this is also inherited and uses the closure property. The other associativity property, which has to do with the field action, was this one, ABV equals ABV, where here we have a field multiplication followed by a scalar multiplication, and here we have two scalar multiplications. So this one, we use 3, which tells us that this element and this whole element here are both in U, and then this element is in U. So there's two elements that are in U by property 3, and over here there's one element that's seen to be in U by property 3, And then we can use this kind of inheritance property. The fact that it's true in V, and so it must also be true in U. Okay. Additive identity. Well, this was just an assumption. And that's true because we assumed that 0 was in there. At least the inclusion of it, and then the fact that it satisfies the same axioms is also because it satisfies the axioms in V. The axioms that an additive identity should satisfy. For additive inverse, we could maybe think about it a little bit more. So let's let U be a vector in U. By field axioms, I know that there's a special element there's a special element 1 in the field, and there's a special element -1 in the field, right? Well, not as special, but there's an element -1, the additive inverse of 1. And so -1 of U is -U, and that's in U. A little bit later, we'll see how to be a little bit more careful about saying things like that. Okay, by closure under scalar multiplication, we have the additive inverse. Multiplicative identity. Well, there's really not much to say there. U is in U. The fact that 1 times U is equal to U follows immediately from the fact that it holds in V. And finally, the distributive properties. Well, these, we could also say that they're inherited using additive closure and multiplicative closure. U plus V is in U, and the addition is the same, and the scalar multiplication is the same. So as long as all of these expressions make sense, they must have the same answers. Okay, so let's look at some examples. So take my favorite vector space of arrows in the infinite blackboard with common origin. Common origin here. So let's think about first a line which passes through this common origin and goes off to infinity in each direction. Is that a subspace? Yes, that's a subspace. 0 is in there. If I take a vector and another vector, I can add them together and get a vector which is in that line. If I take a vector in here and I scale it, I also get a vector which lies on that line. So that's a subspace. How about just the origin? Yes, that's also a subspace because it has the 0 in it, and we saw last time that you can make the 0 vector into a vector space over any field. How about that one? Is that a subspace, including going through the origin? It's not. Why not?
Because you could add vectors within that subspace to be outside of the subspace.
That's right. So I could take a vector like that and another vector like that. I add them together, and I get something which is not in the subspace. Similarly for scaling, right? I have to be able to draw an array. If it touches any point, all those points have to be in it, right? Because of the scaling. OK, so that's not a subspace. How about that guy? Also not a subspace because it doesn't contain 0, and also because, well, let's see, take that vector here, add it to itself, and now we're outside the space. OK? How about the whole infinite plane? That's also a subspace. Every vector space, both 0 and V are always a subspace. So how about in 3 dimensions? If I have now a 3-dimensional space, I pick an origin, I take a line through that, that's a subspace, and I can take a plane through that, that's at any angle, that's a subspace. If I curve it, or if I go away from the origin, it's not a subspace anymore. Okay, let's do another example based on one of our examples from last time. So we talked about the space of, or the vector space of univariate polynomials. Over a field. I'm going to call that space f bracket x. That's the space of univariate polynomials over the field. It's just notation for that. Remember, that's the set of all functions from f to f that can be written in the form bunch of coefficients times x to some number of powers up to some highest coefficient, which is non-zero, the highest non-zero coefficient multiplying the highest power of x. And this m is called the degree of this polynomial p. So I'm going to define a subset. So that's our v. And I'm going to define a subset u of this. And I'm going to denote it by f of x, f adjoint x less than or equal to d. And that's univariate polynomials of degree less than or equal to d. Univariate polynomials of degree at most d. Okay. Is that a subspace? What do you think? Who thinks it's a subspace? See a show of hands. Not a subspace. We're 100% undecided. Okay. It is a subspace. Which we can see by checking this criterion. So let's see what it looks like. 0. So the first part of the criterion had to do with the 0 of the vector space. What's the 0 of f of x? It's that special polynomial, which is 0 all the time, the constant function. Right? It's the 0 polynomial. That is clearly in f of x less than or equal to d, because its degree, by this definition, is 0. Okay? So its degree is 0, and 0 is less than or equal to any positive integer. I guess I should say here, d is not negative. Okay. Okay, 0 is in there. So we've got the first one. Now we have to check additive closure. So if u and v are in this space, that means u and v are polynomials, and they have degree at most d. So they're polynomials. They can be written out this way, and I don't have to write any more than d plus 1 coefficients. The highest power of x that appears with a non-zero coefficient is x to the d. If I add 2 such polynomials, I get a new polynomial. It might have degree smaller than d, right? I mean, if I have p and I add it to minus p, I get 0, which has smaller degree. But it's not going to have larger degree. Okay? You can think about that by just thinking about, OK, we're adding these things. Like we can add the coefficients individually. And there's no way to get a jump in degree. So that certainly implies that u plus v has degree at most d. Third, look at the field elements, we'd like to imply that the scalar multiples are in there. That's true because if I take any polynomial and I multiply this polynomial by a scalar, that's the same as multiplying each of the individual coefficients by the scalar. That can make the degree go down in the special case that I multiply by 0, but it can't make the degree go up. Okay, so that's true. Okay, so that's a subspace. Let's look at another example. Yes?
Should it be a u, or uing f of x less than originally?
Yeah. In this case, I mean to set these equal. OK, so we spent some time on this example of real valued functions. So functions from the interval 0, 1 to r. Have picture like here's 0, here's 1, and here's my function. It doesn't have to be continuous. It doesn't have to have any special things, but it has to be defined at each point. And we figured out how to add and scalar multiply in that by just adding and scaling multiplying, pointwise. We defined f plus g by defining its value at x to be f of x plus g of x for x in the interval 0, 1. So there's lots of this is a very big space. It has lots of subspaces. Here's an example. So let's let this be V. Let U equal real valued functions on 0, 1, which are 0 at some point inside. How about at 1/3? Real valued functions which take the value. So f is in U if f is in V, and f of 1/3 is equal to 0. Right, that's the condition. Clearly a subset. Not all real functions have that property. And I claim that it's a subspace. So we have to prove these three things again. First of all, the 0. The 0 vector in V is that special function which is constant, which is always 0. It's just the function, no matter what x I put in, I get out 0. Okay. Certainly, this function, let's say it this way, 0v is in U. Right? It's 0 at 1/3. So it satisfies this condition. Secondly, we want to check addition. So let's let U and V be in U. That means U and V are two functions of the unit interval that take value 0 at 1/3. If I add them together and I evaluate it at 1/3, by the definition of addition in this vector space, it's U of 1/3 plus V of 1/3. Both those are 0, so that's equal to 0. Okay? So that one is satisfied. Similarly, if A is a field element and U is in U, we want AU of our special point, 1/3. This, by definition, is equal to A times U of 1/3, where the multiplication is in the field now. U of 1/3 is equal to 0 in the field. A times 0 in the field is equal to 0. These are field zeros. Great. OK, so that satisfies the criteria. And it is a subspace. OK, so now what I want to talk about is careful proofs of almost painfully elementary properties of vector spaces. So this is often a point of confusion for students. Things look obvious, and it's almost a confusion. How do I even prove this? It's so clear that it ought to be true. Okay? So let's recall. I'm just going to write up here the definition of a vector space, a very abbreviated version of the definition. Additive abelian group with a field action. What were the properties? Commutativity. That was one of these properties, u plus v equals v plus u. We had associativity. There was a group associativity, u plus v plus w. I'm omitting the qualifiers here, quantifiers. Okay? And there was another associative property, which is this one. It has to do with the field action. There's an additive identity, which is that there exists a 0 in v such that 0 plus v equals v for all v. There's an additive inverse property, which says there exists some negative v in v for all v such that v plus negative v equals 0. There's a multiplicative identity property, which has to do with the field action that says 1 times v equals v. And there are distributive properties. The distributive properties are over here because they're properties of the field action. A times u plus v equals au plus av. And a plus b applied to u equals au plus bu. Remember, addition in the vector space, scalar multiplication. Over here, 2 scalar multiplications followed by addition. Addition in the field followed by scalar multiplication. 2 scalar multiplications followed by addition in the vector space. And that these 2 things are equal and these 2 things are equal. Okay, so that was our definition of a vector space, condensed. And using that definition, we want to prove a couple of simple properties of vector spaces. The first one we could call a cancellation property. Okay. So proposition, let's call this cancellation. Suppose V is a vector space. U, V, and W are vectors in V. And U plus W equals V plus W. Now I'm going to give this a label so that I can refer to it later. I'm going to call it equation 1. And the theorem says that then U equals V. OK, so this is a good example of something which seems incredibly obvious, right? So if you're an elementary student working on their arithmetic can figure this out, right? When I'm talking about adding numbers together, integers or apples or something, right? The point is that because we're in a new situation, we can't take such things for granted. We actually have to figure out why they're true. Okay? So let's do a proof. And the proof has to use these properties, because it's a property of all vector spaces, right? OK. By the additive inverse property, the additive inverse property guarantees the existence of something, right? It guarantees the existence of an inverse for every vector in the vector space. The vector we'd like to get rid of here is W. So let's make sure, let's use its inverse. So this guarantees the existence of, let's call it Z, which we should think of as minus W, such that that is some special vector such that W plus Z, or W plus minus W, if we want to just think of minus W as a name for it. Okay? But at this point, we don't need its uniqueness. We just need its existence. such that w plus z is equal to the 0 vector in the vector space. That's the additive inverse property. And let's give that equation another number, number 2. OK, so period. So let's start manipulating things and try to get u to equal v. So we start out on one side, we write u. U equals something, and on the very end of this, it's going to be u equals v. Right? But there's going to be a bunch of intermediate steps. And every intermediate step we're going to justify. U equals u plus 0 v. That's my first step. OK, so this illustrates a couple of things. One is that in math, you have to be creative, right? So this is a wacky thing to do. I started out with u. I added nothing to it. What's the point of that? Okay, so the point is that if we're trying to write one thing and make it equal to something else, it usually means we have to create a bunch of rephrasings of that first thing. We have to write it in different ways, manipulate them, apply laws until we get to the other side. Okay, so we're sort of expanding it in order to get to our destination. Now, I used one of the properties of vector spaces to write that equality. Which property did I use? One of these properties. Yeah. The additive identity. That's right. The additive identity is a special 0. Anytime I add something to it, I get back the thing I started with. OK, so I'm going to label each of these. Additive identity. OK, let's continue. Let's rewrite 0. 0 is equal to w plus z, where z is my additive inverse of w. And what did I use here? I used equation 2. That's right. Justifying every equality. Now, well, I'm going to want to rearrange things. You see here, there's a sum of 3 things. What property can we use? Well, this property has to do with those, so let's use that property. So even if you don't know what you're doing, sometimes you can do a proof by just writing things down, applying the properties you know, and trying to kind of randomly walk to the answer. Right? OK, so this is by associativity. Now we can apply this equation, because we've made appear on the board something which this equation applies to. None of these do necessarily. Right? So now we can use of u plus w. We can substitute it for v plus w using equation number 1. So this, by equation 1, is equal to v plus w plus z. Right, just substituting according to this. Now I'm in another situation where I can change my parentheses, possibly profitably. So let's just do that. And that's justified by using the associative property again. Okay. Oh, but look, OK, so now we are back to this wz, which we know special things about. We know that w plus z by equation 2 is equal to 0. So hey, we're getting close, right? That's v plus 0. Now we have one less step using, again, the additive identity to get to v. OK, so we made a long chain of seemingly obvious statements that led us from led us from u to v. OK, essentially that's what a proof is, right? It's a long chain of obvious things that prove something not obvious. OK. Anyway, so what do I want to? I want to make some observations about this that has to do with what I expect from you and what a proof is. OK, so I was a little sloppy about this, but first of all, I at least attempted to use, in the combination of speech and writing, proper English grammar. So when you write a mathematical statement, you write a proof, you should use punctuation, you should use periods and words. You should be able to read it like you're reading something else. I use lots of these notations here, which is fine. You could also write these out. You could say something like, u equals u plus 0 by the additive identity property. Either one is fine. It's sort of up to your individual judgment, which is more appropriate for the situation. This is often nicer to read, unless it's a really long chain of equalities, in which case this might be nice to read. Of course, this is faster, which is often a priority in an exam, right? OK. So we used English. Every time I claim something existed, I justified it using a property or using a previous statement. Every time I claimed two things were equal, I justified it using a property or some other equation, some previous thing. So every time something exists, every time something is equal, every statement we make has to be justified. Even seemingly obvious things are justified, right? Like this associativity, wow, that seems obvious, right? But OK, it's a property that of this object. We can't assume it. And we have to even justify the most obvious things. Now, part of doing a mathematical proof is deciding at what level you want the proof to sit, right? How much background do you expect your reader to have? That's a moving target as we move through the class. So in this very beginning, in the first few weeks, I really do expect you to tell me why it's OK to regroup like this. By the time we're 5 weeks in, I expect you not to do that. Right? You don't need to do that. But in the beginning, we're proving the basic properties, so you have to keep track of those, and you have to say exactly why each thing is true. And as we move on at level, there's more and more that you can assume from there. So there's a bit of judgment, and the judgment is what things do I need to justify, and what things can I assume I know, or the reader knows, or the reader knows that I know. OK, that's the appropriate level. But when in doubt, please do write it out. Especially in the beginning, I will take points off for things which are not fully justified. OK, so this is a really handy proposition, cancellation. Of course, it's not really a property of vector spaces. It's a property of groups. So all I used were group axioms. I didn't really use any of these other axioms. But it has lots of nice corollaries that we're sort of using. But let's justify them formally. So there's different kinds of results. There's corollaries, which are things which follow quickly from some other result. There's propositions, which are kind of unimportant things, or things that are not that critical. There's theorems, which are like the big things that we're very excited about. There's lemmas, which are used on the way to theorems. There's even weaker things like observations, which are like, I'm embarrassed that I have to write this down. But it's true, OK. So corollary. The special vector 0, the additive identity, is unique. Special, this is the additive identity. OK. So we could prove it's unique using cancellation. Suppose it wasn't unique. I had 0, number 1. That plus v was equal to 0. That's equal to v, sorry. And so suppose we had one 0 for which it worked, and we had another 0, which when added to v equals v. Well, then, by transitivity of equality, which we can rely on, or we can write down if we want to be really careful, and then by cancellation, by our cancellation proposition, 0, 1 equals 0, 2. So there was some discussion online about that, why that type of thing would be true, and there's an answer. Here's another corollary. The additive inverse is unique. So how do I prove that? I say, well, suppose U and W are inverses of V. Again, this is one of it's just using the group structure. Then we have that V plus U is equal to 0. And V plus W is equal to 0. And this looks almost exactly like our cancellation thing, right? Then V plus U equals V plus W. And by cancellation, U is equal to W. So therefore, the additive inverse is unique. Let's continue in the last 8 minutes proving a couple of further easy things. Of course, with all these type of things, there's usually more than one way to prove it, so we're just picking one way. So let's make this a proposition. Let V be a vector space and A be a field element. Then for all vectors V, we have things like, well, 0 in the field times the vector is equal to the 0 in the vector space. We sort of used that already, but let's justify it carefully. Second, here's one of those things that looks obvious. When you think about it, requires some justification. And the third thing I want to put in here is that any field element times the 0 vector is equal to the 0 vector. Okay. So let's start with the first one. Again, we're going to get creative with our rewriting and do something that seems strange at first. I'm going to take 0, V, 0 in the field times the vector, and add it to itself. And start rephrasing. This is equal to 0 in the field plus 0 in the field times V by what property of vector spaces? Distributive property. And that's equal to 0 in the field times the vector by field properties, right? That 0, this is the additive identity in the field. So that can be rewritten like that. And then that by additive identity, I can add in more 0 vectors. Additive identity. I can add a 0 vector to that number, or that vector. Get something else which is equal. OK. And now I'm in a situation where I could apply cancellation. This is equal to that. Two of these things are the same. I can cancel this with that by my theorem. And that shows that 0f applied to V is equal to 0 vector. Okay. Let's look at the second one. Now, what does the second one say? Okay. One way to think about what this says is I'm given some vector V, and it's scalar multiple A. By the additive inverse property, I know this has an additive inverse, right? And the name of its additive inverse is minus whatever it is, right? That's the middle one here. That's the guaranteed additive inverse of this. So what this says is that here are two other things which also play the role of additive inverse. We proved a little bit ago that the additive inverse was unique. So if I can show that this plays the role of an additive inverse, satisfies the equation this plus that equals 0, and this satisfies the equation this plus that equals 0, then they must be equal to this by the uniqueness of the additive inverse. So what this says is there's three ways to get something which is an additive inverse. They all play the same role. So let's do the first one. We'll say that A, V, the thing we want to cancel, plus minus A times V. So we want to show that this quantity is equal to 0. That will prove that this is as good an additive inverse as any for that, and therefore it must be equal to this. So that's equal to A plus minus A of V by the distributive property. And that, by additive inverse in the field, equals 0 in the field times V. And by the previous one, the first line there, that equals 0 in the vector space. Okay. So that shows that this is just as good an additive inverse for AV as this is, and therefore these two things must be equal. And similarly, you can do it for the other one. So in particular, if A is equal to -1, we get this fact that we mentioned earlier, which is that -1 applied to V is equal to -V. That is, I can always get the additive inverse of any vector by multiplying it by -1. Scalar multiplying it by -1. To get the other one, A times -V. So I want to show that this is also a good additive inverse for AV. I can write this as A times -1 applied to V by the associativity property of this field action, right? There's a -1 buried in there. I can change it around. Sorry, that's not the associativity property. That's this fact. This is the associativity property. Let's call this 1. 1. Well, we already used 1. Let's call it 4. By associativity, I can move this around. A times -1 applied to V. Right, that says that I can either apply the field action twice, or I can multiply in the field and then apply the action. That's equal to -A of V. So that shows that this last thing is actually equal to the first thing, and then by this argument, that's equal to that. Okay. And the very last one, let's do it like this. A times 0 in the vector space. We'll do another weird thing where we add 0 to itself. Distribute. So this is additive identity in the vector space. This is the distributive law for the action. And we also know that A0, A times 0, is equal to itself plus the 0 vector. And so we can apply cancellation to obtain this by canceling off the extra copy of A0, A times the 0 vector. OK, that's all for today. And on Wednesday, after our quiz, brief quiz, we will have sums and direct sums.